Welcome back. We're going to be continuing the 1 billion row challenge that we were working on literally 3 hours ago. Yeah, 3-ish hours ago. And yeah, this is basically a continuation of that. So we're exactly where we left off. In fact, this is literally the last commit, which was I guess that commit message is wrong, but that's okay. Us just changing the sum from an I-64 to an I-32. What is our current run time? So if we just run this, what do we get? We get to wait. Okay, we get 30.8 seconds. Wow, I think that's very different from what we got up here. Pretty far back. Yeah, 37 seconds up here. So 30.8 is kind of crazy. I guess there's just it's highly dependent on noise. Yeah, just gonna run it again to make sure. But yeah, so it's 30.6. That's weirdly good. Okay. Let's do a perf record on this just to get a good idea of where we're spending our time. Just let that run for a few seconds, and then we'll kill it. And then we will we'll perf report on this bad boy and see what we get. So, obviously our time is all spent in start, all called in main. Fantastic. Okay, so 78% of our time is spent in entry. That's obviously a very, very large amount of time. Also, we're spending a weirdly large amount of time in add assign. I'm not sure what that's about, but maybe we need to break that out into maybe we try removing that trait and seeing if that helps. And then we're obviously still spending a fair amount of time in parse temp. I want to see if maybe we can SIMD that. I don't have a lot of experience with SIMD, so I'm not sure how well that'll work, but I mean, we'll see. But I do want to switch gears and look at this hashing, because obviously within here, all of the time is being taken by doing the hashing and then doing the actual lookup. So let's look at the hashing. So how can I come back? There we go. So in Rust, if we look at the hash map, there is a third parameter here that very rarely needs to be passed, and it takes the hash, I guess it's the hasher builder that is actually used to create the hasher, which is what is used to ultimately go from some structure into an integer, a U64, I think, that is actually required for, if we look at the finalize method, finish method, it ends up with the U64. And that is what is actually ultimately used by the hash map to figure out where to put this item, or to look up where this item is. So right now, the standard library uses this random state hasher from stdhash, but it's from hashbrown, which is good. It's a very good default hasher, but it's also designed to be somewhat cryptographically secure, I think, but it's also supposed to be resistant to hash denial of service attacks and that kind of thing. Like it's supposed to be fairly secure of a hasher, but we don't need all of that. We just need something that's fast. So there's a crate called a hash, which is fast. It's also apparently also DOS resistant. But like you can see what it does is it provides a new random state hasher, which is kind of what we want to do, except we're decided not to use third-party libraries, so we have to implement one ourselves. So let's do that. Where is our hash map? Hash map is here. We need to say with capacity and hasher. And then we can say a hasher builder. I guess that's probably not a great name. Let's do, I don't know, quick hash. And it's not the hasher, but it's the hasher builder. Because we have to have a struct hasher, or I guess quick hasher builder, which implements hasher builder or build hasher. For quick hasher builder. And then the only thing that it needs to do is provide a quick hasher. This is effectively like a factory pattern in Rust. And struct quick hasher. Hasher, Jesus. Use 64. Yeah, that'll work. And we can say impl hasher for quick hasher. And there's two methods that need to be added. One is finish and the other one is write. So this is gonna be self.0. And then bytes, or write takes in just a slice of bytes that we can then apply to our hasher and do whatever we need with it. But we'll do that in just a minute. So we're gonna say quick hasher of 0 or something. It doesn't necessarily need to be 0. Like the internals of the hasher itself don't matter. It's purely this function that actually matters. So, I mean, the most straightforward thing that I can think of is to say bytes, or I guess bytes dot as chunks. We'll convert it into an array, or convert it into a slice of arrays, which we can do like that. And then we can do let chunks and rest is this. And then we can loop over the chunks. And then with this chunk, which is now a U8 slice, U8 array, U8 by 8, we can do like U64 from native Indian bytes, like this. And then all we have to do is like self.0 XOR equals, I think is, I mean, it's not going to be a good hashing algorithm, but it is a hashing algorithm, I guess. Actually, let's do let buff, I guess last. This is going to be what we do with the rest. So it's going to be 0 U8 by 8. And then we're going to do last copy from slice rest. And all that this will do is just put rest into this last thing, or into this last array. And then we can do .iter .chain, just so that we also iterate over that. Copied. Or can I do into iter here? I don't think so. Yeah. Or I can, it just doesn't do anything. So let's see, with this, we're gonna go from 30 seconds. I wouldn't be surprised if this ends up being a little bit slower. but I suppose we shall see. And there are, I mean, there's effectively an infinite way that infinite number of ways in which you can make this hashing work. But that being said, I don't think that this is gonna really improve anything yet. It ends up being significantly worse. And that's just because we have a really bad hash implementation. So an ideal hash implementation would spread out numbers like a lot. So like going from 1 to 2, like passing in 1 versus 2 would end up with completely distinct numbers, which our algorithm does not currently do. I think we can maybe improve this by doing like self.0 times equals, I guess let's do n, I don't know, by n. Like it's either way, it's not going to be a whole lot of super useful. So while that's running, let's go look up fast hashing algorithm. I don't really want to just like grab it from a hash or some other just crate and copy their implementation because that feels a little bit cheaty. If we can find like I mean, latency for small keys of random size. XXH3. Like, honestly, I'd be okay with just finding like an algorithm on Wikipedia or something and then implementing that. Oh wow, this seems to be quite a bit worse. I feel like we've been over a minute. We're right at a minute. So no, this is also bad. Let's see, what is a murmur hash? Murmur hash. And for the record, I have literally no experience with like hashing at all, so I am very likely to be getting some or hitting some rather like beginner stake or beginner issues. But let's see. So key, length, and seed. In this version, all arithmetic is performed using unsigned 32-bit integers. In the case of overflow, the result is reduced modulo 2 to 32. I mean, okay, we can do this. So this is 32. Do they have a version for 64? Or does a murmur hash even exist for 64-bit? I mean, in fairness, we can, you know what? Let's just do this one. This is the first one that I looked up. Hash functions can be vulnerable to collision attacks. Yeah, and this is okay. Implementation of murmur hash using a randomized seed are vulnerable to so-called hash DOS attacks. Recommend using their safe hash instead. I don't care. So these are just constants. We can say, can I do a constant here? I don't think so. We can do U64. These are like actually calculated to be good, I think. So we probably don't change them. Yeah, we can't do that. We have to implement a little quick hasher. I mean, not that we can't change them, but we probably shouldn't change them. That being said, we're gonna change them. We're gonna change it like so. No, like so, because why not? Okay, what's the other stuff? So R1 and R2 are 13 and 15. like that. And then some more random numbers. Okay, so that is the constants. Hash is supposed to be seed. So that is basically what you do here. Because we want it to be random, let's choose a random number. No, let's do super random. So open SSL rand. I guess we need what? So we have 8 bytes. So 16. That feels long. Oh no, we have 8 bytes. Wait, yeah. Oh no, this is I see. This is number of bytes. Like that. Bam, random number. You know, actually, since we have a fixed number here for the hasher, it would be more stable as we run it and do like timings. That's just an interesting thought. Okay, then for the actual implementation. So k equals 4-byte chunk, basically this. So what is k? Okay, this is the definition of k. Let mut k equals this. Or I guess this is k. Mut k. K times equals self C1. K dot rotate left self R1. Okay. K times equals C2. And then now we can update our hash, which hash is self.0. XOR is that dot rotate left R2. That times self M plus self N. And self R2. And do that, sure. Okay. With any remaining bytes, do okay, I think what we have right now is fine with how we're handling this end. What do we do afterwards? So for finalize, we do this. So length is not really a thing. I don't know what len is supposed to be. I guess that's probably the length of the key, which we don't have. I mean, we could keep track of it. I don't think it matters, but we're going to find out. So self.0, no way to return it. Self.0, XOR times self.0, self.0. Oh, actually self.0 is not mutable. So self0 here, self0 here. This is mutable. This is hash. Sure, do that. Sure, do that. It doesn't matter. Actually, wait. In fact, we also want to do U32 here. And these are going to be by 4. And these are going to be U32. Wait. And then for actually combining them at the end, I want to do hash as U64 shifted by 32. ORed with hash as U64. Let's do hash as U64. Just so we don't have to keep doing this. And then, so this will basically duplicate the hash. But what I want to finally do is mix in hash shifted by 16. So now we have like basically if hash is like 4, then we end up with this, that, and then we also take the top half of the hash and or like the hash and we do that. It's a little bit weird, but it does a decent job, I think. Cannot multiply that, right? So this is U32. Cannot multiply U32 by U64. These are still, yeah, these need to be U32. And this needs to be smaller. Was that the correct? No, it was not the correct cutoff. That's fine. Now, if we run this, so we're still trying to beat 30 seconds with the default hasher. Okay, so we technically beat it. You know, let's add a hash. Not with the intention to actually like ultimately use it, but just to see what like we can get to. Random state. Oh, new. Oop. Nope. If we cargo B and run it. Then what can we get? Yeah, okay, so with a hash we cut our time in half. So what hashing algorithm does a hash use? Full comparison with other hashing algorithms can be found here. So fx hash actually seems to be a little bit faster for U64s, but we do have more than U64s. However, so we have more than U64, but the average length of a key is what? Like it tends to be fairly short. Like that's 8, or 7, that's 3. We have a lot of really short strings. So like U64 is a bit more indicative of what we're expecting. So I'm almost tempted to like fx hash SM hasher status quality test. I don't know what that is, but it says it fails. I also don't care about unkeyed, or I don't care about like DOS resistance. I think let's try fx hash. Fx hash. I'll go. I mean, like in reality, we could just like steal it from here. Does it have a Wikipedia? It does not. A fast, non-secure hashing algorithm. Great. Is it only um a Rust crate? What is this? A speedy hash algorithm used within Rust C. The hash map and lib alloc by default uses zip hash. I don't know what Rust C data structures is. Oh, unless that's like actually just for the compiler. Yeah. If this is actually just in the compiler, where's the? Oh, it's literally on Rust website. So if this were on, it'd be really nice if we could just use this. Let's see what fx hash does and see what kind of performance we can get from this. So we did. Actually, let's go back to the toml. Let's remove this. Fx hash. Fx build hasher. New. What can we get from this? $22 seconds. So that's actually slower than a hash. That's honestly surprising. Okay, so a hash is good. I think we've discovered this. Oh, wait, there's multiple fx hasher fx build hasher. Wait, what is this build? Because there's a number of hashers in here, and some of them seem to work better depending on the input data, which makes sense. But how do I obtain a hasher 3? I guess it's got default. Or hasher 32. Let's do... Wait, wait, what is... Build hasher default? Wait, what? Why does that go there? Oh. Interesting. Wait. Oh, I didn't even realize this. Okay, so this creates a build fx hasher. I want a build hasher default. I didn't realize that was a thing. Over fx hasher 64. New. And we're still trying to beat 30 seconds here. Or I guess not really 30 seconds. The A hash implementation took about 16 seconds. Yeah, okay, that doesn't seem to have changed anything. Because I mean, honestly, with how much faster A hash is, which I already moved from the tumble, like, I almost just want to grab it and be like, yoink. Because it is just so much faster. So I think we're going to do that. And then maybe we can tune it a little bit more closely to our needs. Yeah, that seems fine. Hopefully it's not too complicated. Oh, wow. Maybe it is. We're going to find out. Okay, so we've got a struct called a hash. What's it called? It's called a hasher. Oh, it's good. No, it's got random state. And then random state implements build hasher. Yeah. Oh, and it returns an a hasher. I was right. So a hasher comes from a hash, which is the crate we're in. Oh, I see. That's documentation. Pub use crate AES hash hasher. If x86 or 64, and we put AES and we're not a mirror, yeah. So we're gonna use the AES hasher, or a hasher from AES hasher. A hasher. I mean, let's just do this, I guess. I don't care about testing. Mod libc. Mod a hash. It's basically going to end up with this. It's going to end up requiring a bunch of stuff. So first of all, we've got PIU128. PIU128. This thing is this. I don't think we need this function though. Normally hashes are created via that for fixed keys or random state, new for random generated keys. Okay, we're going to use a hasher default to produce a hasher. So anything here that produces a hasher can go away. That goes away. Yeah. See, this is part of the problem is, I mean, it is a full crate, so everything is like using everything else. From random state can go away. Test with keys can go away. All of this stuff can go away. Or actually, what does default do? Oh, this doesn't include the default. Where's a hasher default? This guy. Random state with fixed keys .build hasher. Fantastic. That's fine. We'll use new with keys. I don't care. Actually, we'll use from random state. This should be, let's see. What does random state hold? This guy in lib holds on to the random state. Nope. Random state comes from here. Definition of random state is somewhere. There we go. Bunch of U64s. So oh, okay. So this convert is going to convert an array of U64s into an array of, or into a single 128, or into a single U128. So we can say keys is U64 by 4. Standard mem transmute. Transmute, sorry, keys. And it's a U128 by 2. This is obviously a dangerous thing to do, but it is fine since they're the same size. Safety. These types are the same size, and they have the same memory layout. So this is keys at 0. This is keys at 1, keys at 0, XOR keys at 2. Or keys at 1. Okay, we need to implement hasher, or import hasher. This can go away. We already know that we have this pointer size. That's fine. And then add in length. What is that function? So we should be in AES hash in in here. So add in length is a function from operations. Configuration all x86 64 SE2 or not SE2. Oh, this is just using I mean, okay. Ah, like that. You can go away. You can do cell. Oh, this needs to be here. Great. Read small. That's a lot of stuff. Given a small less than 8 byte slice, returns the same data stored in two U32s. Order of duplication of bytes is not guaranteed. Returns the same data stored in two U32s, but it returns them as U64s. I mean, okay, this isn't terribly special. I mean, I guess we can keep the inline always too. Okay, and this can also be inline always. Inline always. Compiler should almost certainly inline him automatically, but this is fine. Data read the U32. I mean, it does data dot array. No, there's a way to get just the front away or front array front array. I mean, I guess read array works. And then we do U32 from any bytes. Expected U64 find U32. Right. Or, I mean, we can even just do dot into. Then we duplicate it, and we get U32 from any bytes data 4. Or wait. So we're not guaranteed that it is 8 bytes here. All we're guaranteed is that we have some number of bytes. So it should be data.len minus 4. Expected U8. That found result. Right, this needs to be on wrap. Actually, no, you know what we can do? We can do data to 4.try into .unwrap. Try into for an array will I think do the bounce checking, which is a little bit annoying, but I don't know a better way to do this. So it's fine. It's good enough. Okay, if we have 2 to 3, then we're gonna read a U16. And a U16. If data.length is greater than 0, then we have bytes, or then we have a single byte. Otherwise, we have just 2 empty things. Okay, that's fine. Why are you complaining? Okay. Very nice. Now, self read small. Value here is a U64 by 2, but hash-in requires that. So that's going to be standard mem transmute. Read last U128 by 4. Wow, there's a lot of stuff in here. I really hope I don't regret, like, bringing this in. If we go back to AES, where does AES encode come in? Comes from operations. What is this transmute macro? From 0 copy. I don't understand what this is for. Okay, I feel like this is ultimately just using the same thing as transmute. So we'll do that. We'll do that. Transmute. Transmute all of the things. Okay, read less you. Let's do AES deck. I'm gonna do basically the same thing. Okay, read last U128 by 4. So U128 by 4 is 64 bytes. There we go. So this is gonna be data dot. I mean, to be fair, I think as our chunks. Splits the slice into a slice of n element arrays, assuming that there's no remainder. But there's no... Oh, I guess because of the remainder, you have to do as R chunks. Right, there's no way to do unchecked there. That's fine. So we can do as R chunks. Dot as sorry, dot zero dot as r chunks. Wait, so this is the last 4 chunks, or this is chunks in reverse order. The remainder is meaningful in division sense. Yeah. What is the order of chunks though? Okay, the order of chunks is still the same. So if we did r chunks dot 1 dot as r chunks, so this one's going to be 16 for the U128s, and this one's going to be, actually no, you know what, 64 dot 1 at data dot, fuck that, let tail is tail at, or dot last dot unwrap. No, I don't want that check. I want to do tail at tail dot len -1. Okay, so now we have tail as U8 by 64, and then tail can be U128 by 4 with standard mem transmute. Like that. Okay, add by 64. I mean, ultimately, all of these functions kind of just become like transmutes, and they end up calling a single like CPU instruction. Convert. So it takes a U128 and it turns it into 64 by 2. Which is what this function takes. Yeah, what is the point of turning it into whatever? It's fine. We'll keep the transmutes in here. I think we kind of have to. But yeah, that can be fine. And then this returns U64 by 2, but it needs to be whatever. So standard mem transmute. There are so many transmutes in here. It's kind of crazy. So add by 64s, I guess, can also just straight up return a U128. That way we don't have to do the unsafety here. Okay, shuffle and add. Shuffle and add. Oh my god, is this the first function that doesn't use transmute? Oh, but it uses convert, which is basically transmute anyways. So shuffle is this function. This can go away. It's just a.swap bytes. Really? We'll just do this in line. Okay, and then add by 64s takes U128. Shuffled is a U128 already. Which means we don't need to transmute. To add is already U128. We're already returning a U128. Read U128 by 4. That's what we're doing here. Almost. Instead of being R chunks, it's going to be as chunks unchecked. And this is okay because we're only reading a single chunk. Safety. Len is greater than 64, and we read a single chunk. Okay, so that can go away, that can go away. Or no, wait, no, that's literally necessary. This is head. Head, 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 head. Read U128 by 60 by 4. Returns a rest. Which I'm gonna assume is just let rest is data from 64 onwards. And then this is called blocks. Oh, and this doesn't have a remainder, obviously. And this is actually going to be 0. So this is going to be a U8 by 64. This is a U128 by 4. Cool. And then part of transmute is that it'll actually assert at compile time that the size is correct. Okay, so this one's going to be, so it's U128 by 2, which is 32. Also, this is called head. Oh, I guess tail is still in scope up here. That's questionable, but that's fine. That's a thing. We don't care about rest here. We don't care about current either. Tail here is called head. This is 32. This is U8 by 2. Expected U128, found U8. Oh, because this is called head. Beautiful. Finally, read 128. Read last U128. Okay, we're going to do basically the same thing again. And for like the second to last time. So this, it's that. This is going to be 16. This is going to be 16. This is head. Yeah, this is head. This is tail. Hello? Okay. And then finally, hopefully, for the very, very last time, we do U64, U64, 8, 8, head, tail. Oh, and this literally does... I guess this one's slightly different because head and tail don't necessarily... they can overlap. So I think that this is fine. This convert is bad, though. It needs to be standard mem transmute. Although I thought U128 had, like, from parts or something. Maybe not. This needs to be unsafe. Okay, we're getting closer. We're at the finish line. Sort of. We have quite a bit more to go. Actually, no, this is all for specialized stuff. Okay, AES deck gives a U128. Sure, standard mem transmute. Unsafe. Transmute. Great. Config specialize, config specialize, config specialize, config specialize. Everything here goes away. Beautiful. I love deleting code. This is just wrong. Oh, no, it's not. This just doesn't need to exist. Okay, so random state doesn't exist anymore. Cool. Now we need to, we're not going to bring in random state, but we're going to look at how it generates its seed. What is const random? That seems interesting. Const random. From a crate called const random. No. Just generates a random constant. That's actually super interesting. I didn't know that was a thing. That's not what I care about though. Let's go look at random state new. So get source, get fixed seeds. You know what? 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 Default build hasher default for a hasher. And let me make sure that this is gone. New. And then a hasher. Impl default for a hasher. And we're going to do some magic. Open SSL rand hex 16. Let's use some random numbers. I really hope that after doing all of this, we actually do get fairly decent hashing. No. But there's only one way to find out. Transmute used without annotations. I don't fucking care. So 16 seconds is what we got with a hash, like from its from the crate itself. And 30 seconds is what we got with our shitty little hashing algorithm. So we got 24. That's not awful. It's a little bit sad, honestly, that we got that instead of, I don't know, something better. Let's see, under operations, what is the, maybe not under operations. I want to see where they get, like, read U128, read U16. Where does this come from? Oh yeah, GitHub's gonna be fucking useless, isn't it? Crate convert. Yes. Read from slice. Okay, how does read whatever work? Self split at 2? Oh, that's from the front. Okay, yeah, read from the front is easy. Read from the end. Okay, so it literally is a split at. Yeah, so that's not going to be any more performant. Interesting. I wonder why ours is quite a bit worse. I mean, if we bring back this function, yeah, let's do that. Let's say self from random state. Keys are going to be generate this, generate this, generate this, generate this. Like that. Beautiful. If we run, does this get any faster? Is there some weird pattern with the keys that we want? Okay, so no, that was slower. That's great. What if we run it again? I'm not at all concerned about these like unnecessary transmutations, just because the transmute is literally free. Like transmuting is just for the type system. Okay, so that did actually just make it slower. And to be fair, this could be const fn. So then now we're not actually computing that like XOR and stuff. I don't know that that would really cost anything, but maybe. Nope. Damn. Okay, so we're gonna go back to what we had before. Although, okay, actually, no, you know what? Let's continue down this, how do they generate the keys question. So if we go back to random state, new, it's got this get source function, which gets a random state source, or random source. The get fixed seeds just generates some random numbers. No. I mean, yeah, no. Get fixed seeds does this. So PI UX 64x4. And this guy. Okay. And then what is the other part of this? Self from keys. Wait, wait, what the fuck? It creates a hasher to create the hasher. Okay, we can pursue this. Write usize C. C is what? C is the usize. Great. What? Where does this get called? Gen hasher seed. Okay, that just seems to be a random number. So let's do the 16. Wait. No, 8. Also, what is K0, K1, K2? So from keys has A and B. Okay, so A is fixed at 0. Okay, so let K0, K1, K2, K3 equals fixed seeds at 0. And then we'll create the new hasher like that. And B here is can you do destructuring here? I don't think so. Fixed seeds. I mean, to be fair, we can just say this is pi ux. I say pi. I don't know what that actually stands for. And then B here is going to be pi2. Like that. And then that can go away. Okay, so we're trying to beat like the 26 seconds that we were just having. Let me remove some of these unnecessary transmutes while that's running. Transmute user. Let me also disable this because Clippy is going to be a little fucking annoying. Unnecessary transmute. Okie dokie. What? What do you mean? Oh, from B bytes. Or from any bytes is fine. Same thing here. Same thing here. And then we can get rid of this because we know that this is garbage. Where were we? You go away. You go away. Okay. 29 seconds. So it just got worse. I think we're just continuously making it worse. I mean, what happens if we literally just return this hasher? I mean, 26.3 isn't awful. I'm a little bit unsure as to why we're getting significantly worse than just using a hash by itself. And also, like, this can be const. Mm-mm. I mean, this is definitely not great, right? Like, this is... I think we actually... I think we should fix this. So, we did discover down here. I say discover. We ultimately ended up with something more like this. Which is just a touch better, I think. Maybe. I don't know if the compiler can, like, reason about this. But it's fine. So U32 is 4. U32 is going to be head dot, or I guess U32 from NE bytes overhead. And the same thing here for tail. This is going to be, break it into 4. And this is going to be U32. No, wait. This is that. This is going to be head dot. No, sorry. This is going to be U32 from NE bytes tail. Like so. And this is head. This is tail. Yeah, and then into. Okay, then we do the same thing for U16s. U16, 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 2, head, tail, into. Great. I don't know that that's going to change anything performance-wise, though. Yeah, it's pretty much the same. This is actually really annoying because I feel like we are really close. I'm not sure. I just don't know why this hash implementation is quite a bit worse than the other one is. How does it hash? Okay, so this is for the full array. So we never do a byte. We never do a U16 or a U32. We don't do U128s either, so we can just remove these. They don't really matter. Yeah, so no change. Ugh, this is really annoying. So the thing is, this case is so rare, right? Like the vast majority of our data is going to be here. Or it's going to be like here. I almost want to like just try changing this and say let value is a U8 by standard what is it? U1 or yeah, standard mem size of U128. And then we'll say value value dot copy from slice. And we're going to copy from input. Then we're just going to use self.hash in value. Value here is that U128 from NE bytes. I wonder how this improves it, or if it changes anything at all. Okay, so that made it slower. Great. In fairness, we are now copying data, whereas before we weren't. And we're putting a bunch of zeros into the machine, whereas before we weren't. Another thought I have is to do like this. Or wait. No, it's super weird. I'm gonna change the music. Hold on. Late Night Vibes. That's our new station. Okay. Let's do a little bit of a perf record on this. Just to see if maybe there's something that it can highlight that is like standing out massively. While that's running, actually, let's take like a 5-minute break and we'll be right back. And we're back. Okay. So I have run perf record. Let's do a perf report on this and see where our data lies. Wow, this is taking a minute to run. Wow. Does not normally take this long. I guess we're gonna be waiting. Oh. Hey, look at that. Oh. Okay. The stack trace might be a little bit buggered, I think. Yeah. Okay. Let's do a perf record again. This seems to happen sometimes, and I'm not entirely sure why. I'm not, in fairness, I'm not super familiar with like perf, but I don't know. Yeah, see, it did it again. Okay, so we have start. And in here, yeah, we just have like the pointer, but not actually the name or anything like we're supposed to have. I'm so confused. Do you really want to exit? Yes. Cargo be released. Like generally it fixes itself by just re-recording, but it okay, so it fixed itself this time. Now we've got this. No. Wait. Oh, we can in our toml, let's do panic is abort. We don't need all the panic machinery in here. Kind of forgot about that stuff. Yeah, we're still spending most of our time doing hashing. Most of our time is in... Can't even see it. How do I want to see the full name. This is a very long name. I don't know. So find inner is calling this, whatever this is. What did I do? Whoa. Wait, what did I don't know what I did. Yeah, there we go. Okay, wait. No, why? Okay, let's redo this with panic off or panic abort. There we go. Okay, main has hash map, has this. So make hash. And then whatever this is, I can't see the name. Show header information? No, that's not terribly useful. Yeah, I don't actually know what this ends up being because it goes off the screen. Can you use a mouse in here? No, you can't. Okay. But that's fine. If we look in it, This gets called. This gets called. A bunch of comparisons get called. Interesting. I guess one part of what we're doing that is not great is that we are doing a bunch of string comparisons, which take time. But I would think that the hashing still is slower than that is. Although make hash is only 19.54%. So it's interesting. So here's an idea. We have, so what is a stir? A stir, like a slice. A slice is a pointer and a length, right? Like you can represent, we're gonna switch thoughts from the hashing for a minute. Sort of. You can think of the struct that holds our bytes as a slice, or as a pointer, and a length. And technically, it could also be a pointer to a slice. It's the same thing in Rust. No, it's not. I take that back. That's a fat pointer. We don't want a fat pointer here. I mean, we could. It doesn't really matter, I think. But this alone is 16 bytes. And since each of our strings is like less than 16 bytes, not all of them, but like generally they seem to be less than 16 bytes, we can just store it in the same structure. So we can use a union. JSON syntax is not valid. Great. Small stir. I think this is basically what small stir is. Small stir is a thing, right? Repr. I've never actually looked into it, so I could be wrong. I don't want to look into it because I don't really think we need to. So small stir is going to be a union between a bytes. Actually, how do unions work in Rust? I don't actually know. I have never needed one. I think you I think you declare fields. Grab the field and type manually drop. Yeah, it can be copy. Great. Yeah, you're right. Right, so we have bytes, and then alternatively, we have, or I guess let's call this slice. And then alternatively, we have bytes, which is going to be a U8 by 16. Right? No. Yes. No. This doesn't quite work because we lose the size. We could make it like 15 and give it a U8 for that, where the U8 here is the size. And then I think repr or repr packed is the default. Oh. Although Rust representation is fine too. Okay. That seems like this is a weird type, but I think it's fine. Yeah, and I don't really see an issue with this. It is a little bit questionable because how do we differentiate between whether it's a slice, which I guess we can represent as a U size and a star const U8. Like how do we differentiate between these two variants of this union? So for those who don't know, a union is multiple data types that are represented within the same area of memory. So like in this case, if we have an instance of this this small string, then this like we can access dot slices dot 0, or we can access dot bytes dot or I guess slices dot 0 refers to the first 8 bytes no matter what. So that's either this U size, or it's this U8 plus the first 7 bytes of this array. So if we do impl from U8 for small stir, then we can say if value.len is less than 8, I guess if it's less than or equal to 7, it's probably a little bit better. We can say let bytes is 0 by 15. Yeah, okay, so I think the way we represented it is if the topmost bit of bytes at 0, if top bit of bytes dot 0 is 1, then we have bytes. Otherwise, we have slices. And that's okay because... Fuck, that's not okay because of little endianness. Okay, wait, hold on. If we do this, then it's okay. Right, because the topmost bit, or not the topmost, wait, hold on. Thinking. Yeah, the topmost bit here is not the topmost bit here. That's, no, I take that back. Sorry, I'm very confused and I'm confusing myself. What is the representation here? The representation is 1, 2, 3, 4, 5, 6, 7, 8 bytes, and then the length. Representation here is 1, 2, 3, 4, 5, 6, 7, 8 bytes. Oh, wait, sorry, no, I'm wrong. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, and then the length. Representation here is 8 bytes for the pointer. And then we have the length in little endian, meaning that the bottommost bit, or bottommost byte, is the highest. So this guy is the highest byte. Yes. And so if the topmost bit of this U8 is set, that means we have bytes, and that's okay because we're never going to have a size that is quite that large. Okay. That seems fine. I think that's fine. We're going to find out if that's fine. So if value.len is less than 7, then we're going to say let bytes is this array. And then we're going to say bytes up to value.len.copy from slice value. No. Yes. Copy from slice value. Then we can do small stir where dot bytes, no, this is not C, where bytes is that bytes and its value.len plus 1 shifted by 7. So that sets the topmost bit. Otherwise, we're going to do small stir. Can I do value.into raw parts or something? Standard slice raw. Like I want to convert it into the raw parts. Value.as pointer. It doesn't even matter. We can do as, so small stir. Where slices is this, or slice, not even slices. And then value.len. Cannot, that's fine. Okay, so this will pack the data. So I think that should be fine. And then we should be able to say impl as ref u8 or small stir. And then we're going to say if self.bytes.1, and it's unsafe to access this field because, like, obviously we're this is effectively a transmute. Dot, is there a way to get the top bit? 7 equals 1. Then we're gonna say standard slice from raw pointers, or from raw parts, self as const, self as const u8. And this is obviously unsafe. At this point, I think I've given up on writing safety comments because who cares about safety? This is going to be self.bytes.1 ended with, I guess, 0x7f to remove that, like, top bit. And then we finally cast it to a usex. Corrected u8 slice found that. Otherwise, we're going to do standard slice from raw parts. And this will be self dot bytes. No, wait, self dot slice dot pointer or dot 0 self dot slice dot 1. Now this theoretically should work. Let's write a quick test for this. So it implements from a slice of like 0, 1, 2, 3. And then we can assert eq ss as ref 0, 1, 2, 3. Just a quick. Okay, so that one worked. I'm gonna be honest, I'm a little bit surprised. There. Okay, so we can do 1, 2, 3, 4, 5, 6, 7. Actually, let's do a quick macro. Macro rules ss test. Slice is going to be this, and this is an expr. and that goes there. And then we can say ss test. In fact, we can even do, this is going to be comma separated. That way we can do something super fancy like that. And then here we can do 0, 1, 2, 3. And then just like keep going 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And then I want to check a single, check an empty. I'm going to be honest, I am very surprised that that works. And also I take this back. Because I want to be able to use strings here. Or byte strings specifically. So I can be like, hello world. Maybe if I spell things correctly. Like that. Okay. I'm really surprised that that just immediately worked. I'm going to be honest. I'm completely flabbergasted. But the benefit here is that we're no longer dereferencing any sort of data to just do this. Creation is a little bit costly. That is true, but it's not that big of a deal. Yeah, that it's not that big of a deal. And then, creation is costly because we have to copy. But then actually accessing it is effectively free. Then we can say impl hash for small stir. Standard ops hash, I think. Maybe standards hash. And then we can say self as ref dot hash state, which will continue hashing the slice. And then now what we can do here is use a small stir and do, so entry here. Yeah, I think we can do a small stir from here. Branch prediction, probably not going to be too harmful with this from. Oh yeah, small stir also needs eq. I guess partial eq. And the way we can do this, so we can either just like use as ref here. I think what we can also do is if we have the pointer and the length, if they're the same size, then we know what do we know? Then we know that we're looking at the same slice, but we don't need to actually do anything on it. So let's do our actually let's move this to be a function. And let's also do inline always here. Is bytes. And it's basically this check. Parentheses are required to parse this as an expression. What? Where? Oh. Okay, that's weird. Anyways, self-move due to this call. I guess this can take by reference. This should be derive clone copy though. Can you even derive eq and ord for a union? I wouldn't think so. What do you need ord for? Oh, because we sort by it later. That's fine. So here for eq, if self is bytes, or if we are not bytes, and other is bytes. So if we're not bytes and the other is not bytes, then self dot slice dot 0 equals other dot slice dot 0, and other dot or self dot slice dot 1 equals other dot slice dot 1. Okay. Otherwise, self as ref, eq other as ref. Okay. What else? What else do we need? We need center comp. Oh, right. We've got partial eq, but we need eq, which we can just derive. That's fine. And then we need ord. Expected that found small stir. Okay. Now, what are we trying to beat? 31.6? Really? I thought it was lower than that. Either 31.6 or 27.0. I don't remember if we undid that change. And I honestly don't even know if this will really do any improvement. Oh, I probably should have committed after we did the hashing changes, which honestly didn't do any improvement either. Yeah, I feel like this isn't helping. Oh, wait, I'm perf recording. Okay. Well, that would explain why it's taking so long. So another thought, since this is definitely taking longer, yeah, for eq on small stir. Wow, that's definitely taking a while. Um, if self is bytes and other is bytes, then self bytes transmuted to U128 should be the same thing as other bytes transmuted to U128. Wow. This is significantly slower. Okay, that's weird. That should have worked. Oh, I guess it might be under like cargo. Yep, just sitting there spinning its own core. Or spinning its own thread. That's weird. It's definitely, yeah, it's been 2.5 minutes already. Yeah, I don't think this is it. You know, I'm honestly really surprised. Oh, fuck. Also, this doesn't work. This is wrong. I take this back. This is wrong. This is not a guaranteed approach. This works. If this works, then the other stuff doesn't matter. However, this is very rare chance in here, so I'm going to say we don't need that. Basically, this is like, just undo it. This is, if this is true, then we're equal. Not if this is false, then we are not equal. Right? If it's false, it doesn't necessarily mean we're not equal. But this part is true. Which meant it basically just kept re-adding to the hash map. Though I'm gonna be honest, I feel like we're still taking too long. "26 seconds. Never mind. I take that back. That was already an improvement. Transmute does require that they're the same size. Compilation will fail if this is not guaranteed. Okay, so like if I did a U64 here, this fails to compile. Yeah, okay. Good. I'm glad to see that. So this does seem to have helped a little bit. Not a whole lot, unfortunately. I'm not super surprised. I would have expected the help to be fairly minimal. One thing we could try. So actually, something I do want to do. Let mut len is 0. I literally do just want to just see what the average length is. Or which is probably easier to do down here. And then really this can just be iter, it doesn't matter. And then if we run this, don't really even care about the output, but I want to see what the average length is. Seven. It got put into the middle of like nowhere because of reasons, but that's okay. Okay, that's cool. So 7 is our average length, and we can hold up to 15 in our little thing. Oh, actually, that's supposed to be 15. I wonder if that'll change anything. So we were at 26 point something, 26.5. If we hold up to 7, no, hold up to 15 in our little thingy mabob. I know, words are great. It might be a little bit faster, or a little, yeah, even just a little bit faster. No, it's actually quite a bit slower. Really? That really surprises me, actually. I guess we're copying from Slice more. Although, what does copy from Slice end up doing? Copy from Slice impl. I don't know if that bounce check stays, but we can do this. Standard pointer. Source is value. Destination is bytes. And bytes.len minus, I guess literally 15. And this is unsafe, obviously. What was this? I forget. I'm gonna be honest. I don't remember. We can also do out is this guy. I don't know if this will matter, but we can do this, and then instead of doing that, we copy directly into the struct. Okay, Rust Analyzer's freaking out. Yeah, I don't know what that was about. No field that, oh yeah, dot bytes dot 0. Yeah, I think this is more than 30 seconds. Yeah, it's definitely more than 30 seconds. It's a bit surprising, I think. Like if I just say less than 0. I know, Clippy, come on. Like I want to see what the performance is if all of our stuff is in it's just we treat it as slices. So like we had what do we have? We had 26 seconds, I think, with our 7. We can go back and look, I guess. Yeah, so we had 26.4. Okay, we have 26.13. So for some reason, just using slices is faster. Which is weird, because I thought we were using slices before and it wasn't. Right? Like, if we come back down here, and we're like, hey, you're going to use U8 slice. Right? We don't... We just used U8 slice. We got 26.13 before. What are we going to get now? While that's running, I'm going to grab a drink, and I will be right back. Okay, now I'm super confused. Because we're at 25 seconds. And nothing has changed. From like the 30 seconds that we were having before. And like, in fairness, it could just be like my computer's doing other things right now. I'm also streaming and doing all of this stuff. So it's possible that it is just kind of noise. Yeah, now it's 23 seconds. If I keep going, is it going to eventually get down to like -2 seconds? It's going to finish before I press enter. Okay, 25. So it's going between 23 and 25 right now. Okay, let's remove our small stir. Apparently this isn't useful at all. I feel like it might be. It's just that something I'm doing here is not making it so. Or maybe that was a little too early. Still not super happy with our hashing. But I think that's fine. Okay, let's do perf record. And then we'll do a perf report, as one does. Let's see where our time is being spent. So here, 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 here. So add a sign is still using 6.42%. That's not insignificant. Can I annotate that? No, I don't have. Let's add a sign. Let's do a inline never. Go away. And let's do this again. And then we're gonna annotate that. Wait, hold on. We've already done that. It was this sum that was taking a long time. Let's do this. Can I inline to all colors? I cannot. That'd be too handy. Basically, what I want to do is come down here and do that. I don't think that this should change anything. But maybe it will. Not time. I want to cargo. So the only thing that I can see that this will change. Actually, no, you know what? So that was about 7%. Like if I report right now, yeah, it's gone, right? Obviously, because we have manually inlined it now. But if I cargo R, I don't think it's going to be any, no. If I cargo R, I don't think, fuck, I need to time it. I don't think it's really going to be any faster is the thing. It might just be inline, or like we just might not see this, the delay anymore. Because now it's right there. If we go to the station, struct station, this guy, or stats, min max, sum and count. I guess count. So we've got 1 billion, and we can have at most 10K. I don't know if underscores are supported. They're not. We can have at most 10K, which gives us 100,000, right? 1, 2, 3, 4, 100,000. So we can have up to 100,000 in our count. U16 can hold 30 something thousand. This can be an U32. Right, what is what is U16 max? Is it gonna be 65536? Right? 65536. 65535. Right, so we need U32 in order to be able to support the count. So that's fine. Smaller size there, or in that stat struct, should theoretically mean that it can be moved around a little bit cheaper. Because right now it's the size of, I guess it's what, U64, so it's basically 48 bits, so 6 bytes. No. 48 is, I feel stupid, it's 12 bytes. Anyways, pretend I did not say that. Stats. Did we do a, no. Let's see what that did. Just inlining this and changing the count, I guess. And this OR default should be pretty cheap too. This is also const. I don't think I need to manually say it's const, but it is. Oh, I forgot to fucking time it. Time. No. Time. Okay, 25 ish seconds. Not fantastic. Like honestly, I don't really know what more we can do. Like we could, is there a way for us to like SIMD here? Let me do this. Do I have inline never anywhere? No. Let me do inline never here. Inline never. And let's do a perf report dash call graph Dorf here. No. Oh, perf record. And let's take a look at this. So here and here and here. So we have parse temp. I guess this parse temp. If we annotate this. Yeah, obviously this, like the branching in here is pretty slow. Can't say I'm surprised that that is pretty annoying. Surprised that there's nothing for this. Wait, comp. Compared to 3. What is an RDX? It doesn't really seem to say. Oh, is this doing a bounds check? Compare 3 with RDX. Like, that would make sense for that. That's the only 3 that I can think of in here. Is there... Here's a question. Is there, like, get unchecked? There is. Returns mutable references to many indices at once without doing any checks. That's a horrible idea. I want to do it. Yeah, fuck it. Let's do it. Bytes.get unchecked. Get disjoint unchecked. Disjoint unchecked. And I don't need them to be mute, but I don't see any reason to not. Oh, I do. We don't have a mutable reference. Fuck. Okay, so here's the thing that we can do. We're doing some wacky unsafe stuff anyways. Right? I mean, it's really, really bad to be transmuting like a slice reference to a mutable slice reference. Wait. Oh. This goes to here. Like, what's your opinion on Mojo programming language made by LLVM creator? C++, Rust, Python, Zig. I've never heard of it, actually. Wait, no, maybe I have. Mojo Lang. I think maybe I have heard of it. Yeah, but I've never actually used it. So can't say I have an opinion on it. Although that does make my opinion on it immediately, like, not great. Okay, so we have... Oh god, this hurts my heart. Yeah, fuck it, let's keep doing this. Still not open, but they say we'll make it. What? What do you mean? Yeah, the fact that it's not open source. Oh, are these just like... Wait, what is modular? Oh, is that like the people who make the language? I mean, at this point in time, I think any compiler I use needs to be open source. It's not the 80s. We're not paying for compilers anymore. And I honestly just don't typically trust software that's just distributed as like a binary. Okay, I think this hurts my heart too much. We can't do it. I do want to say like fn get or let get is... No, you know what? Fuck it. We'll say get unchecked. Unsafe. Like that. Because we don't actually need the bounds checking here. Like, we know everything here is in bounds. Get unchecked. No, okay, you know what? Let get is takes offset is a usize. And it returns bytes.get unchecked offset unsafe. This is bad code, but I'm okay with it. Get -1 or get 1, and that's going to be bytes.len minus. Yeah, that's fine. This is gonna be get that get 3. Just a little bit of comment so we can like just explain what's going on here. Okay, and then here is going to be get 4. Is it like a slice unchecked or something? Oh no, it's literally get unchecked with this. Yeah, because slicing is just get. Get unchecked here already returns the reference, so we don't need to bother with that. This is going to be get 5. Also, this should just be B. Get 4. And this is also going to be, yeah, fuck it, let's create a slice, which does basically the same thing, except it gets a range. Beautiful. Maybe that's a little bit better. I don't want to perf record. I just want a cargo. I want a time. I honestly don't know that this will have any real performance impact. No, not really. That's fine. At least now we have a lot more unsafe code, which is like super important. We are also inlining still, or never inlining. So maybe that has a mild cost, which I mean, I don't know that it would be too great though. But I guess we're gonna find out. Nope. Literally no change. I mean, technically 200 milliseconds slower, but I think that's just noise. That's fine. Let's do this again, but let's do a perf record. And then let's perf report. Yeah, go away. This guy, this guy, this guy. So parse temp is still slow. Still slow as balls. Why is it so... Oh, okay. Does that remove the bounds check early on though? Where are we? Okay, and parse temp starts here. What is this? Type output equals this. Something here got in line. Oh, this is probably get. Yeah, so dereferencing the pointer is still fairly slow. Multiplication here is slow. That's true. I don't know that we actually have a good way around that though. I wonder if there's a way to parse this without actually parsing into base 10. Nothing that immediately stands out. So jump not equal to 61. 61 here being A. What? No, that's hex. What? Not equal to 61. 61 is an equal sign. Oh, wait. Sorry, no. JNE to 61 is this guy. No, it's the previous comparison. So jump not equal to 2D, which is dash. Okay, so that's the comparison here. It is pretty slow, which is fair. Can we make that branchless? We can actually. How do we do that? So get 5. gives us something. If we do minus, no, if we just do equals b dash, then we get a 0 or a 1. Neg. Then we get a 0 or a 1. With which we can say slice 5 plus usize from neg. So problem here is the negative, I think. Like the negative out. Because it can be out times 1 minus neg times 2 plus 1 minus 1. Out here being an I16, so I16 from neg gets us that. And this is technically branchless, but it is incorrect as well. This needs to be like that, like that. Right, so if we get, so say we get neg equals true, then we get 0 times 2 is 0, minus 1 is negative 1. Okay. Let's see. I don't really expect this to be a whole lot faster, but who knows? So we're going from 25.4. Oh, holy shit. That was so much better than I expected. Okay. I'm definitely not complaining. Wow, okay. I'm genuinely like a little bit, I'm astonished that that was that big of an improvement. I guess this is a pretty common case, which makes sense, right? If numbers can go from minus 99.9 to 99.9, then a very large amount of numbers, like from minus 10 and onwards. So like, what is that? So that's 89. I know I'm just randomly saying shit. Let's see. Yeah, okay. Just the vast majority ends up reaching this bottom case. Yeah, that's interesting. Okay. I'm really glad to see that that had a major improvement. Is there anything else that we can pretty easily improve? So this is the last branch in here, which is really cool to see. And with this one, I'm not sure we can make it better. At least not in its current state. So get 4. Yeah, that's fine. Really the bigger thing is this like return. So there is an aspect here that if we get 4 and we get 5, it's okay because we know that 5 will always be at least a letter. Right, like if 4 is semicolon, then 5 is a letter. So there's probably some math that we could replace this with. But I'm not sure about like replacing this. So let's move on. This check means that this check is not necessary. I think. Let's try on our small data set again. Yeah, seems like that is the case. Though I'm pretty sure that check is also fairly small. I mean, it literally just checks if this range is 0, pretty much. What else? Interestingly, this is the same thing as line.split at, or sort of. It's rest.split at once we have the at. But I'm not actually sure if it's any more better. If it's any better to try to do that instead of just what we're doing here. What does actually, if we do rest.split at, what does it do with the divider? Oh, it includes it in the end. You know what? I think like this, it's basically the same performance. I find that just is a little bit cleaner. Okay. You can also be inline always. It's probably even better. Okay. Let's get our like a final metric here, and then I think we're gonna be wrapped up for today. So 25 seconds. Not awful. I don't know how we wait, didn't we just have 18? I'm so confused. We literally just had 18. And like I wouldn't even say that's noise. Like that's 7 seconds difference. That's like 25% of runtime. $26. What the fuck? I'm so confused. Wait, is it because we removed the inline never? Okay, so now we're pretty consistently at 26. I'm so confused. Like I'm genuinely I'm so confused. We literally just had 18 seconds. And nothing has meaningfully changed on this computer. Like I'm not doing something stupid, am I? It's totally possible I'm doing something stupid, but I really, really don't think I am. I'm, okay. What the fuck? Why is it 8 seconds slower now? I think I literally just have to chalk that up to noise. There's literally nothing else that makes sense. Because nothing else changed. Nope, not that. What's our diff? So we've got a hash, and we've got let's remove this inline never, because that certainly doesn't help. A hash and what did we change? Oh, we changed the panic. More branchless parse temp. Okay. That is in the repository right here. And that is going to be all for today. So thank you for watching, and I will see you next time.